Hey everybody, welcome back. Where we are now, we're at lecture 4.3, so there are only 2 lectures left in the course. This is intermediate and short-term climate variation. So we are working our way from longer-term processes, like those controlled by plate tectonics, to intermediate, like those controlled by the Milankovitch cycles we'll talk about today, and more short-term climate variation, leading up, of course, to a discussion of modern-day climate change, which is also short-term climate variation, a very quick, rapid short-term variation. So we will begin just talking about how we reconstruct past climate, how we know what ancient climate used to be. So again, more recent climate rather than super old climate. One of the things that we do if we are looking to reconstruct past climate is to look for glacial features. And so if we're talking about looking for glacial features, then we're talking about climate probably within the last 500,000 years or so when we see a significant amount of glaciations. So what are some glacial features that we know about, that we've learned about in class, that we might find on the surface of the Earth? Well, hopefully you think back to that particular lecture. It was the wind, water, and ice lecture. What are some of the things we see on the surface? Well, this image here, although it may be a little unclear what's happening, but these are some rocks in Central Park, New York City. Those of you who live in New York may recognize this. But a lot of the rocks in Central Park are covered by glacial striations. And remember, glacial striations are grooves that are cut into the rock that were cut because of rock that the glaciers were carrying, moving that rock forward and cutting striations into the surface. Lots of other glacial features too. We can look for things like moraine. We talked about the fact that Long Island is basically mostly a moraine. Eskers, U-shaped valleys, though we tend not to see U-shaped valleys predominantly in North America. We see more of those in Europe, where we have a lot of mountain and glaciers today still. Glacial till, glacial outwash, those are different kinds of material deposits left over from the movement of glaciers. And so we can see a lot of those all over the country. And the Midwest in particular, where I taught at ISU, Illinois State University, for 5.5 years. And it's very flat there. And the only type of geology or geologic features you might see anywhere nearby are eskers and glacial till, glacial moraines. So a lot of leftover material from the last glaciation. So we can look for those features and we can map the extent of them. And the extent of those features would then give us an indication of how far the glaciers themselves extended. And so this is a map of the maximum extent of the continental ice sheets during the most recent glaciation, and that is compared to today's continental ice sheet. And so you can see for the most part, we have the Arctic Ocean, which is covered by sea ice, a little bit different from an ice sheet itself, but there's sea ice in the winter in the Arctic, and then Greenland, of course, covered by a continental glacier. But if we go back and we look at that last glaciation, you'll see that it was a large extent of ice extending all the way down into North America and in parts of Europe as well. The last glaciation was significant in North America compared to some other places. That's the Laurentide ice sheet is the one that covered North America. And then we have a Eurasian ice sheet, the one that covered Europe, and then also some parts of Asia, but mostly down into Europe. That ice sheet extended as far as 37 degrees north latitude. Here's an image showing you that in a little bit more detail so you can see what this looks like in North America. And again, so here we look at Illinois and Indiana and Ohio, a lot of the Midwest covered by ice during that most recent glaciation. So lots of evidence of that. And you can see same thing for the Northeast part of the United States as well. So a lot of Canada was covered by the last glaciation, but then a lot of the northeastern parts of the United States. So one of the most useful ways for us to reconstruct past climate is with oxygen isotopes. So it's been a while since we talked about isotopes. Hopefully this will refresh you a little bit. Just as a reminder, many different elements, and in this case oxygen is what we're going to talk about, have several different varieties based on mass, right? So there are heavier versions of oxygen and there are lighter versions of oxygen. And so we're going to look at 2 of those. There's also oxygen 17, but we're going to look at oxygen 16 and oxygen 18. And so the oxygen 16 and oxygen 17, when we see low oxygen 16, that's indicative of a period of glaciation. And when we see higher oxygen 16 or lower oxygen 18, that would be indicative of an interglacial period. I'm going to explain how this works in just a minute. But you'll often see figures that look something like this. And these are figures that are reproducing the oxygen isotope history over time. And so we are, in this case, the most recent time here at 0 is on the left, and we're going back 500,000 years, as you can see, 500,000 years at the other end of the diagram. And so oxygen 16 higher at the top, lower at the bottom. And so that's also a way of looking at that would be the ratio of oxygen 18 to oxygen 16. So here are periods where we have high oxygen 16, right, which is indicative of low ice volume, or therefore it would be hotter in the interglacial periods. You can see indicated by the red. And then low oxygen 16, or thus higher oxygen 18, is what we see during periods of glaciation, so colder times in Earth's history. And you can see that again indicated here by the blue. And what you'll notice, excuse me, is that there is a pattern of increasing and decreasing ice over time. So we have periods of glaciations, and then we have what we call interglacial periods. Those are indicated here on the second diagram, where we have the ice ages, the interglacial periods, and we have another ice age, interglacial, then we have another ice age. But how do we know that, right? How do we have this 500,000 year record of global climate, you know, based on ice? How do we have that, right? How are we able to use that? So to explain this, I'm going to have to go back to the drawing board here, the literal drawing board. So I'm going to open my whiteboard. There we go. And we're going to talk a little bit about how this works and how we can use oxygen 16 and oxygen 18. Okay, but again, remember, two types of oxygen, oxygen 16 and oxygen 18. So what I'm going to do here, we'll see how this turns out. Never can be certain how my drawings are going to go, but we're going to draw this in green again. Keep forgetting to not make it black anymore. Something that looks like this. So some land that is on the edge of the ocean. And so what we're looking at here specifically is to look at the system of, or part of the water cycle, I should say, that is condensation and evaporation is what we're actually going to look at. So oxygen 18, oxygen 16, let me write that somewhere over here. 18, O, right, and 16, O. So that's what we're talking about. So in water, oxygen 18 is more prevalent. And that is because different types of isotopes like to go to different kinds of places. They like to establish themselves in different types of reservoir. And so heavier isotopes like oxygen 18 prefer to be in a liquid state. So in the oceans, just in general, we have more oxygen 18 than we do oxygen 16. So both isotopes are there. Both isotopes are going to be in every reservoir, but we have more oxygen 18 than we do in oxygen 16. So what happens next in the hydrologic cycle? Well, the next thing that would happen is evaporation to make clouds. This might be my best drawing yet, guys. Now, oxygen 16 is the oxygen that prefers to be in a water vapor state. So there is more oxygen 16 in clouds than oxygen 18. Again, now both of them are going to be there, but oxygen 16 is more prevalent. So oxygen 18 wants to stay in the water, oxygen 16 wants to go to a water vapor. So let's imagine that these clouds are moving along. The next thing that would happen in the water cycle in terms of what we see happening in clouds is we might get some rain, right? My raindrops are never very good here. Oh, that's not too bad. So we've got some raindrops. What do we know about oxygen 16 and oxygen 18 in terms of where they prefer to be? We know oxygen 18 prefers to be in a liquid state rather than a water vapor state. So when we rain out oxygen or rain out water, there is more oxygen 18 in the rain than there is oxygen 16. So this is oxygen 18 heavy rain going again back into the water, which means then that we're taking oxygen 18 out of the clouds and leaving oxygen 16 behind, so that oxygen 16 is still more prominent than oxygen 18, but it's significantly more prominent by this particular period in time. Okay, so higher oxygen 16 in the clouds than oxygen 18. That's always going to be the case. So the more rain you get, the more oxygen 16 you're going to build up in those clouds. Now, let's say that our cloud ends up over land eventually, and let's just imagine that we have moved from like a hotter area to a colder area. So maybe we've moved here from the equator to like North America somewhere, or Europe, right? Some kind of scenario in that case. So we move to cooler environments. Now we still have more oxygen-16, right, in that cloud than oxygen-18. That hasn't changed. It's actually probably more oxygen-16 rich by this point. But if we are on land and we are in a colder environment, then it's not going to rain, it's going to snow. So let me draw some little snowflakes here. Right, so my little snowflakes, because that is solid material, right, are going to be oxygen-16 rich. Okay, so oxygen-18 again likes to be in a liquid, oxygen-16 prefers to be in water vapor and to be in an actual solid state. So that is oxygen-16 rich snow. So more oxygen-16 than oxygen-18, all right? What's gonna happen to that snow? It is going to pile up onto our surface here. So this is my little surface of snow. Indicate that with some little snowflakes, okay? And so that snow then is very oxygen-16 rich. Let me just draw a little arrow here. So oxygen-16 rich snow. Now, that snow over time, right, lots of time, it could eventually turn into ice if it's compacted and become a glacier, right, but a big ice sheet basically. So if it does turn into ice, then we have this oxygen-16 rich ice. So the snow becomes ice. What happens when it warms up though? Because right now we're assuming it's relatively cool where we are on the land. If it was to warm up, then what happens, or what would happen, is that oxygen-16 from the ice is going to melt and is going to go into the oceans. And so then we're going to be adding oxygen-16 to the ocean water, and thus changing the overall relationship between oxygen-18 and oxygen-16 in the oceans. So when are we melting oxygen, or when are we melting the ice to put oxygen-16 into the oceans? We would be doing that in what we call the interglacial periods, right? So those are the periods between the glaciations, interglacial periods. I don't know if you can hear my wife in the background. She's in the other room on a phone call. I don't know if you can hear both right now. But during the interglacial periods, that's when things warm up. We put more oxygen-16 in the oceans. So if we were to measure ocean water during interglacial periods, what we would see is that we have more oxygen-16 than we do oxygen-18. So high oxygen-16 during periods of interglacial periods, okay? Now the converse would be if we were in a period where it was an glaciation, so it was very cold overall, which is basically what we just drew. So if we're during a glaciation or a glacial period, that oxygen-16 is going to remain in the ice. It's not going to melt, and therefore the initial composition of the seawater is going to remain the same. And so in that case, oxygen-18 is going to be higher than oxygen-16, okay? So all we have to do is we have to be able to measure the isotopes in the oceans over time to get this information. You may be asking yourself, well, how in the world are we going to do that? We're looking at 500 million years, right? Or 500 million years, really 500,000 years of geologic time. How do we find that in the oceans? What we do is we take sediment cores, right? So we would drill a core down into the ocean. We would pull that core up. Cores usually have layers of sediment. Remember, sediment is deposited over time. We pull that sediment core up, and then we can look at all the individual mud, or whatever it happens to be, but probably most likely mud, within the core, get the oxygen isotopes in the mud, and that's telling us then the oxygen isotopes of the water at that particular point in time. And so we can reconstruct the climate history of the glaciations and interglaciations, specifically using sediment cores and measuring oxygen isotopes. So again, the key here is, do we have more oxygen-16 or do we have more oxygen-18? Okay, so actually I'm going to stop there, and then we're going to come back in a minute and talk about Milankovitch cycles. So I will see you in just a minute.